We look at some examples from section 4.3. We'll start off with number 12. Okay, so on number 12, they tell us that f of x equals 2x to the 6th minus 3x to the 4th. On here, it tells us to sketch a graph of the following polynomial, identify local extrema, inflection points, x and y intercepts when they exist. Okay, so basically what we would start looking at here is we would start looking at what are our possible zeros. So for our x-intercepts. Our x-intercepts are going to happen when their original function equals 0. So if we factor out an x to the 4th, we see we have 2x squared minus 3 left equals 0. So x equals 0. Once again, here we have our 0 of multiplicity of 4, or as we used to call this, a quadruple root 0, or a 4th root. Okay, and then we would have this where we would take 2x squared minus 3 and set it equal to 0. So if we add 3 divided by 2, that's 3 halves, takes the square root. We get our plus or minus the square root of 3 halves, in which then we could clean this up into being plus or minus the square root of 6 over 2. Okay, so we see that we have 3 zeros happening here. So once again, so we can get some approximations on here. If we look at the square root of 6 over 2 as an approximately 1.22. Okay, so approximately 1.22. So what I'm going to do is I'm going to pull out a second sheet of paper here and just kind of start listing things off, because this work's going to get messy. We got to try to be as organized as possible on here. So we see x-intercepts are when x equals 0 and plus or minus root 6 over 2. Next thing we're going to start looking for is we'll start looking for our local extrema. So that's when we're going to take our first order derivative. So if we take our first order derivative here, we see we have 12x to the 5th minus 12x cubed. Now taking this and setting it equal to 0, we can factor out 12x cubed. And factoring out 12x cubed, we get x squared left minus 1 equals 0. So we see that x equals 0. And then once again here, this would be a triple root, or we would see it 3 times. And then we would have our good old add 1 over, take the square root, and we get plus or minus 1. Okay, so we're seeing that here we start listing our maximas and minimas as we start considering what's happening on here. Then bringing in here, okay, so I'll go like this. Local max slash min, x equals 0, and then plus or minus 1. Once again, some values that we will be considering as we keep going through. Now we'll take our second order derivative. Okay, so if we're looking at that 12x to the 5th then, minus 12x cubed, taking that would be 60x to the 4th minus 36x squared. As we go through and we would solve this, let's see here, we could factor out, if I take 12 out, so 12x squared out, that leaves me with 5x squared minus 3. So we see that x equals 0 right here. Once again, a double root, or 2 times multiplicity of 2 on here. Then we would see that we would add 3 over, divide by 5, so we'd have 3 over 5, and then that's at x squared. So then taking the square root plus or minus. So we see we have plus or minus the square root of 15 over 5 when we would simplify this. Once again, giving us a little approximation to go back to on here for our graphing. If we just going to delete off what I have here, could have retyped everything in. Once again, over 5, we get 0.77. So we see it's approximately 0.77. So we see now in here that we see that inflection, or I'm sorry, concavity, deals with 0 when x equals 0, and then when we also have plus or minus root 15 over 5. Okay, so we have some things that we start working with on here, once again with our intervals as we're looking at it. So we tell us to identify local extrema, inflection points, x, y intercepts when they exist. So just given this information that we have right here as we kind of went through, we can kind of start looking at our graph. Okay, and what we know on here, I'm just going to go like this, space it out a little bit more. You know, this would be my 1, 2, -1, -2. We know that at 0 and then plus or minus 1, okay, we have zeros on this graph. So that's our x-intercepts. Nope, I'm sorry, that was my local maximum minima. We got to go back here at that 1.22. Okay, so let me just thicken this line here. Look, it's like almost like white out, but with black, where it's just a thicker line. So we would look right here would be a 0, and then right here. So once again, that 1.22, -1.22 for the approximations on there. Then we would start looking at, well, at -1 and 1, we would be seeing some local maximum minima. But if we're noticing, we have 0, 0, 0. So we're talking about maximum minima, concavity, everything in here of what's possibly going on with our change with our overall function. Once again, also noting that when we have this root 15/5, which once again was at 0.77, so 0.77 and -0.77, this dealt with a change in our concavity. Okay, so what we could be seeing overall, once again, because this is an even function, when I plug in my -x, I see an even function. Should be some sort of y-axis. Also going back to n behaviors, if we were to consider the limits on here, we would be at infinity and infinity going both ways. We would see overall on this graph, it would be coming down. Okay, so we'd be coming down. Once again, having a 0 here. At this here, we would have what would be a local minimum in this case, in which then our curvature would start changing right here to level off to that, coming back to that 0. Once again, because this is a 4th root 0, means that we are not going through the 0. We'll be coming back off of it, in which then we would see then that our curvature would change down to another one, and then we would thus then curve upward. So we would see some sort of graph happening like this, where we would have critical values at these points, once again, where our slope is changing from decreasing slope to increasing slope, and then once again we're going to change to decreasing right here. We see that overall the concavity right here doesn't change for what's happening with this. We still stay concave downward, even though it showed up in our concavity test. But once again, because we had a value that kind of appeared everywhere, special things happen at those cases, so we have to take it in stride of what's going on. So basically these values here is kind of what's going on, and we could go through and find what y values we had in our functions and graph this a little bit more precise, but we just want an overall kind of knowing what x values are happening here. Let's take a little bit more in depth. Once again, let's look at number 16 for graphing purposes. Okay, so number 16 here talks about f of x equals x squared over x squared minus 4. Here we're going to go through our full guidelines, graphing rational functions, and then we're going to determine what's going on. Okay, so we consider what's happening here. We have to look at our overall domain. Okay, so we're going to identify our domain. So if we look at our domain, we have the domain as a set of reals such that we have to eliminate out when is this denominator going to equal 0. So once again, x cannot equal plus or minus 2. Once again, when x squared minus 4 equals 0, we would add 4 over, take the square root, so it's a plus or minus 2. So we see that our domain is on the interval from negative infinity to negative 2, unioned with negative 2 to 2, union with 2 to infinity. Okay, once again, this is our overall domain, so we're seeing that we have some vertical asymptotes at this. So once again, I'm going to do my work in one spot and do my graphing elsewhere. So if I come here for my overall graph, so we can kind of see what's happening on here, we see that when we're at, go like this, and we'll go out to 3. So I have 1, 2, 3, negative 1, negative 2, negative 3. We see that at 2 and negative 2, we're going to have vertical asymptotes going on because they are undefined on our original function. Next thing that we look at as we graph, we start looking at, is there any symmetry? Okay, so whatever going on here, for symmetry, we would look at f of negative x. So that would be a negative x squared over a negative x squared minus 4. So that is x squared over x squared minus 4, in which then we see that is our original function. So we see f of negative x equals f of x. So that tells us that this is an even function. Okay, so that even function means that whatever going on the right side of this graph is also going to be going on the left side of this graph. So we should be seeing some sort of y-axis symmetry as we're graphing this. So as we see 2, negative 2 kind of popping up on both sides with that symmetry, and there should be happening to continue on. The next thing is we're going to have to perform our first order derivatives and our second order derivatives for this. And then we'll have to find our zeros. Once again, performing the derivative on this, sorry, I need this piece of paper back. F prime of x. We could look at it a different way. We can't really break it apart, so we have a quotient rule. So now we got to apply our quotient rule for division. So quotient rule for division is going to be low d high. So x squared minus 4 times 2x minus high d low, okay, all over the square of what's below. So once again, low d high minus high d low all over the square of what's below. In simplifying this, once again for time purposes, let's see here, I have this answer written. As we would simplify this, we would get a negative 8x over x squared minus 4 the quantity squared. Okay, once again, just distributing out and looking at this. Given this, now we would want to perform our second order derivative of this. So the second order derivative of this would be a little bit more complex. Once again, time purposes, we can go through this, but I don't want to bog down on an hour-long lecture that you need to watch in here. So for purpose of what's going on, we would have 8 times the quantity of 3x squared minus 4 all over x squared minus 4 cubed. Okay, once again, we would square the denominator, it would be like a 4th power. but when in the process of everything going on in the numerator, we'll be able to factor out and cancel down. So that's why it's only a cube power in here. If you have more questions on that, you can contact me and I can show you precisely how I came up with that answer. So as we keep going on here, once again we have our first order derivative, second order derivatives. We're going to find when are these equaling 0. So we want to find when does f prime of x equal 0. Okay, so once again f prime of x is going to equal 0 when negative 8x is going to equal 0. Once again, when that numerator equals 0 is when the whole overall function equals 0. So we find when x equals 0. Okay, so this talks about a local min slash max, depending upon what's happening on here. The next part we talk about is we talk about when does f double prime equal 0. So once again, that would be when our 8 times 3x squared minus 4 equals 0. Sorry, I wish I could read my notes. This was a plus sign back here. Okay, so we see that there are no zeros here because divided over by 8, I'm going to subtract 4 over divided by square root of a negative number. We aren't going to have that, so there are no zeros here. So what we see is that the concavity doesn't change. Concavity doesn't change. Okay, so we see in whatever going on with our graphs that our concavity staying pretty constant in whatever sections we're graphing over intervals. There's no changing concavity points throughout this graph. Let's see here. Next thing on our list, identify extreme values and inflection points. So once again, there are no inflection points on here. We don't see any doubling up from here to here, so there's nothing questionable on this. But we are going to be looking for, is this an actual local maxima or local minima? So if we were to consider this overall problem, please remember that second order derivative test from the previous lesson talked about if we take f double prime of 0 and we plug it into here, we see that we would have 8 times 3 times 0 squared plus 4 over 0 minus 4 cubed. So we see that this is 8 times 4 over a negative 4 cubed. So we're going to see that this is negative 4 in value, okay, or this is less than 0. Because remember, if this is less than 0, that this is negative in value, it's talking about concavity downward when x equals 0. So this is a local maximum at 0. Okay, so once again, at 0, I'm just going to go down here, at 0, we have a local maximum. Okay, once again, that's telling us a critical value on here. We want to work with end behavior to see if we have any vertical or horizontal asymptotes. So once again, end behavior is going to deal with that original function. So we're going to look at when the limit as x approaches infinity of x squared over x squared minus 4. Okay, so once again, this is the limit as x approaches infinity. We have 1 over 1 minus 4 over x squared, in which then this is going to approach 0. So we get 1 when we plug infinity in. Then we'll look at the limit as x approaches negative infinity of x squared over x squared minus 4, in which then we have the limit as x goes to negative infinity. Once again, dividing everything by that denominator power, that's what I did up here. We get 1 over 1 minus 4 over x squared. So this really is a negative 0 because that negative infinity in there, but once again the sign really isn't mattering with that 0, we still get 1. So we see that we have a horizontal asymptote of y equals 1, once again because we're seeing end behavior in here. So if we come back to our graph, we're seeing that when y is 1, we're seeing that, hey, we have this horizontal asymptote going out here. So we know that as we go to infinity and negative infinity, we're going to be getting close to these values in here. Okay. The next part was looking at actual x-intercepts then. So if we look at our x-intercept, we'll look at when does the numerator, or x squared, equal 0. So once again, x squared equals 0 when x equals 0. Okay, and once again, it's a double root, so it's an even root. So we see that we're not going to be going through this graph, but we will be bouncing off of it. So we see that we have a 0 at 0 right here. Also realizing that this has to be a local maximum. So if it's a local maximum, we're looking at this. Remembering that our concavity is always positive within here. Our concavity never changes as we're going through every point, so this is concavity downward. Once again, if I plugged in any value in between here, we would see that our concavity would be downward. If I come over on either other side, we would see that overall on this graph we have values in here. So if we were to plug in to our first order derivative, if I were to look at, like f prime of negative 3, I would see that this value would be greater than 0. Once again, because I have an increasing function here. Here, if I were to look at f prime of 3, it would be less than 0. If I were to look at f double prime of negative 3, we would see that we have concavity upwards. So this would be greater than 0 here. F double prime of 3, once again, would be greater than 0 because we have concavity upwards. So we start seeing that our graph is defined a little bit differently in the fact that from negative infinity to negative 2 exclusively, we see that we have concavity upward. We also see we have an increasing function. Down here we see from negative 2 to 0, right here, we would see that we would have an increasing function, and then it would be decreasing over here, but we would see from negative 2 to 2, overall we would have concavity downward. Once again, double iterating the first derivative and second derivative test on here that this would be a local maximum. So do realize that when we start going through the graphs on here, they are going to be very detailed. We're going to be looking for inflection points when our concavity is changing and graphing those points in here, and also our local maximum minimum points. Please remember, for any point that is graphed on here, x is going to equal some value. What we do is we go back to the original function with that value to figure out what our y value is, because then we would have our xy point that we would start graphing on here. Once again, as these problems get more detailed and they get more complex.